I will be talking about a proposal we have developed to measure contextuality in a hierarchical way. So this work has been introduced by Etibar and myself in this paper. We are at the moment also thinking of in which other ways different to what I'm going to present specifically today we can think about this hierarchical. In contextuality by default, we do work with systems of random variables where each of these variables is double indexed. We identify them both by the content, say the question they respond to or the property we are measuring, and the context, that is the conditions under which they are recorded. So we can represent this set in the way that is written in the lower part of this slide, in which we are identifying what properties are being responded to in which contexts. And within these systems of random variables, we are particularly interested in two classifications or two types of subsets of these systems. One is the subsets that we call connections corresponding to content Q, which is the subset of variables that respond to one and the same content, which, as Eti also mentioned, are stochastically unrelated. These any two variables within one of these subsets do not possess a joint distribution, and the whole pursuit within contextuality by default is in the relationship that we can make between the couplings we can impose to these connections or to pairs of variables within these connections in isolation and the corresponding couplings that we can impose with them considering their contexts. The other type of subsets that you are interested are given by the contexts. Sometimes in the papers we do call these subsets bunches, and these are the subsets of random variables that are measured together in the same or in some well-defined way within the same context, for which we do know their joint distribution, whether it is predicted or defined theoretically, how they are jointly distributed, or something that we can observe experimentally by performing some actual measurements. And in the following, I am also going to restrict our presentation to systems in which we have a finite number of contents and a finite number of contexts in our system, and in which all our random variables are binary, let's say taking values 0 and 1, although we can also take these labels arbitrarily. When we have such a system, then we can represent a specific system of random variables that has some particular distributions of them by using three vectors, which basically are the same that Etibar mentioned, using the expectations. Here I'm just going to use the probabilities. So the first vector here, L star, contains the probabilities with which each of the random variables in our system takes the value 1. The second of these vectors, here called C star, is completely determined by L star and contains the probabilities that describe the maximal couplings for each pair of random variables within each of the connections. This maximal probability is determined by the minimum of the two probabilities with which the two random variables of the pair within each of the connections can take the value 1. And the last of these three vectors, we create stacking this sequence of vectors, contains the minimal and set of probabilities that we need to complete, or at least one of the possible sets that we need to describe the joint distributions of the random variables within each of the bunches. And here we are just explicitly separating in this vector the probabilities that correspond to the pairs of random variables, the triples, and so on. So when we look at the vector b star sub 2, we are looking at the known probabilities with which any pair of random variables within a context that contains at least two variables are both equal to 1. And in general, when we look at the vector b star sub s, we are looking at the probability with which each tuple of s random variables within a context can all take the value 1. Once we have constructed this vector this way, we can more easily see that this vector b star has a nice structure, and well, we are using the descriptor hierarchical structure to also integrate our name of hierarchical measure of contextuality. The first place we can note that the pairwise probabilities for each of the variables in each context, so here we have PC sub Q1, Q2, are bounded below and above by these two expressions, below by the maximum between 0 and this linear combination of the probabilities with which each of the individual random variables can take the value 1, and above by the minimum of these two probabilities. And when we look at the probabilities with which 3 random variables within a context are all equal to 1, these probabilities are also bounded below and above, below by this maximum of 0 and this average of the pairwise probabilities, and above by the minimum of all the relevant pairwise probabilities. And as we move in general, we do have that for each tuple of S random variables, the probability with which they are all equal to 1 is bounded below and above by these two expressions. So below, it's always the maximum between 0 and this type of average, and above by the minimum of the probabilities that included only S-1 tuples of random variables. That is, that we can notice that this vector B star, it has elements that are hierarchically bounded. The elements in B star 2 are bounded by the elements in the vector L star, whereas the elements of B star S are bounded by the elements of B star S-1. So we can use this to approach this measure of contextuality or non-contextuality in a hierarchical way and analyze separately these different levels. Before I move to that, I just remind what was already mentioned at this talk, but now in terms of these vectors of probabilities that I am using to represent the vector, the system. So when we have a specific system of random variables represented by vectors L star, C star, and B star, then we know that it is non-contextual if and only if there is some vector H with non-negative elements, such that this linear system here in the middle has a solution. And when this solution H exists, then H will create a coupling of all these random variables by having assigned the probabilities to all possible combinations of ones and zeros, since I am using zeros and ones as the labels for my random variables in the system. And M in this system of linear equations is an incidence matrix that indicates for each of the rows or each of the elements in the vector which of the combinations of values of ones and zeros of the variables is relevant to the computation of that probability. So in particular, for example, we will have that the first row of M is composed by a vector of ones, because the sum of all these values should be a probability distribution, and being non-negative, they also need to add up to 1, which is the first element in the vector in the right-hand side. And each of the other rows will contain ones and zeros if the corresponding element of H is relevant to the computation of the probability on the right. So if, for example, we take an element of L star P C sub Q, this row or the corresponding row will contain ones whenever the variable RCQ takes the value 1, and it will be 0 otherwise. Now, this system of linear equations we can start to decompose using this hierarchical structure that we found for the vector B star. So we will now split the matrix M according to the vectors on the right-hand side. So we will denote by M sub L and M sub M the elements of the rows of M that correspond to the vectors L star and C star respectively. And we will denote by M sub S the corresponding rows that, the rows that are corresponding to the elements of B star sub S for 2 all the way to R, which is the largest number of jointly measured random variables within a single context. And with this, we will construct the following sequence of nested systems of linear equations. First, we have this system in which we only take the matrices ML, M sub C, and M sub T with the probabilities for pairwise correlations, and we progressively stack additional matrices and subvectors. So we will have a system up to level S and all the way to all of our matrices and the whole set of vectors that we use to describe the system. So we get the largest system here, MH, or the stack all the way to M sub R, HR. As I mentioned a moment ago, we know that a system that is non-contextual is one for which this system of linear equations has a solution, let's call it H asterisk. So the way this relates to this hierarchy of linear systems is that if the system is non-contextual, it is almost obvious that the existence of H asterisk implies that all of the systems in our hierarchy also have solutions. We just need to take H asterisk sub S equal to H asterisk. So whenever a system is non-contextual, all these systems of linear equations all also have solutions. However, if the system is contextual, then there is some value S asterisk between 2 and R such that the system corresponding to that value of S has no solution H sub S, and any further system that had values of S greater than S also does not have a solution. And also, all the previous systems did have a solution H sub S. Therefore, we can further qualify the contextuality of the system. It's not only that the system is contextual, but we can also say that the system is contextual at this level S asterisk. Now, if we are saying that the system is contextual at a certain level, then now we can proceed to try to measure the degree of contextuality of the system at this particular level. So here I am presenting you how we expand or specify or concretize the measure CNT2 that Etibar was talking about a moment ago for measuring the degree of contextuality at the level S asterisk. In general, we can compute this degree of contextuality using linear programming, and the linear programming task that we need to solve to compute it is the one in the table in the upper part of the slide, in which we will find some vector x, it is analogous to the vector h, such that we are able to minimize the sum of the elements of this vector d that bounds the differences between the results of the product of ms asterisk x and the elements of b star sub s asterisk. That is, we are going to minimize the difference of what we can achieve with a vector of non-negative elements that need to add to 1. And each of the probabilities that we have used to describe the S asterisk tuples of random variables. This is subject then to the constraint that all the lower levels do achieve equality. That is, all the lower levels have been possible to be satisfied. That is, pairwise probabilities, triples, and so on, before we have reached level S asterisk. And the measure is just computed by the L1 distance between these 2 points, which we can see easily corresponds basically to the sum of the elements of this vector D. Analogously, for any level that is non-contextual, so S less than S asterisk, and when the system is non-contextual for all of them, we can try to measure the degree of non-contextuality at that particular level. So now we will also define this non-contextuality measure in CNT2 at level S, and it will be the minimum of these D negative and D positive values, which we can find each by solving a linear programming task. In the left, we are looking at the linear programming task for finding the D negatives, and on the right, we have the tasks for the D positives. You can see that basically what we are looking here is how much we can subtract in the case of D negative from each of these probabilities before we reach a contextual system or we reach the limit that was imposed by the probabilities of the level before, the one we are considering. And similarly, these D positives tell us how much we can add to each of these probabilities before we reach that limit or we reach a contextual system. As a way of an example, I would like us to consider this particular system. That's a system in which we have two contexts with three properties being measured in both of them, such that, well, all of them take the values 1 or 0, and their probability with which they take the value 1 is all equal to 1/2 for all of them, and such that in the first context, all the variables are independent. That is, whenever we take events that involve pairs of random variables in the first context, those events have a probability of 1/4. And whenever we have an event that involves the three variables in that context 1, all of those events have a probability of 1/8. And in the second context, we take the variables just to be pairwise independent. If we look at such a system, or rather such family of systems, we can see that all of them are non-contextual at level 2. However, the system will be contextual at level 3 whenever this triple probability, the second context is not equal to 1/8, and in particular in this case, the contextuality measure then will be just given by this absolute value of the difference between the probability and 1/8. The key message with this example is that we actually do have systems that may be contextual at a level that is not the second level. This generalizes a bit the observation that Etibar was making, that we do not need a subsystem that is cyclic and contextual to have a contextual system. And we can actually find systems that for which we need to go upper in this hierarchy before we can realize whether they are contextual or not. And in particular, it is also showing us that it's not sufficient for us to just consider pairwise associations between random variables to determine the contextuality of a system or not. Thank you so much.